Hi, everyone. I'm Chelsea. I'm an assistant professor at Stanford, and I'll be talking about broad data for broad robot generalization. And Sonia's talk is actually a great, there's a great transition because a lot of what I'll be talking about does have to do with generative models of predicting the future, but more focused on robotic manipulation than for driving. So to start off, I've spent a lot of my prior work working on reinforcement learning for robotics, and we could get a robot to learn pretty impressive skills like using the spatula to lift an object. Also a number of other labs have kind of applied these same sorts of techniques to get robots to hit hockey pucks into goals, open a door, throw an object to hit a target, and so forth. And you might look at these and think that we've kind of solved the problem of learning these kinds of skills on real robots. However, we have a bit of a problem here, which is that the robot isn't learning generally how to use spatulas and how to open doors and so forth. It's learning how to use, for example, this spatula with this object, with this background in this environment. And if you wanted the robot to be able to handle a different spatula, for example, or a different environment, it wouldn't be able to generalize to those scenarios because its entire world is this one environment in which it learned the skill. And so analogously, if you were to think about what this would be like for a human, it would be like on day one, giving the infant a spatula and saying, your job is to figure out how to lift this object with this spatula. And so from this perspective, it seems like we probably need to rethink our approach if we want robots to be able to generally understand their world and perform in a wide variety of environments. Now, one way of looking at this problem would be from this kind of machine learning standpoint, where we're essentially training on a lab environment and hoping that we'll be able to get generalization to the real world. And so from this perspective, one natural solution to this problem would be to, instead of training on a lab environment, trying to broaden the distribution in which we are training robots on. Essentially, if we want robots to generalize broadly, we should train them with equally broad data. And this is a recipe that's been super successful repeatedly in machine learning, from computer vision to natural language processing. And it's also reflective of the fact that people accumulate and learn from broad experiences. And so this suggests that perhaps we should figure out how we can train robots, not just on one lab environment, but with much broader data. And so the corollary to this statement is that we need to figure out how we can develop algorithms that can learn from such scalable data sources. And so, for example, if we're developing online reinforcement learning algorithms that need to learn from online experience and collect data for every single new experiment that they do, that may not be as scalable as if, for example, they could leverage an offline data set of their previous experience. Okay, so with this motivation in mind, one natural question that we could ask is, can we use broad computer vision data sets? For example, can we use off-the-shelf object detection systems? It turns out if you take an off-the-shelf object detection system and apply it to a robot like this, you get images that look like this. And these are exactly the kinds of images that, that off-the-shelf models tend to work actually quite poorly on. We've actually tried to run them on these kinds of images, and they generally don't work very well. There's too much domain shift between the kinds of images that people take on the internet and these images, and also many of the objects that you see here might be out of set compared to the objects in kind of a closed set detection system. Another option is, well, we have ImageNet, we have good features, can we fine-tune features from ImageNet? And we've also tried this for robotics and found that compared to learning from scratch, we often see pretty minimal gains from pre-training on ImageNet. I don't know exactly what this is, but kind of my main hypothesis for why this is that in embodied, whenever you're learning with kind of an embodied agent with a robot, you need both a good representation of perception as well as a representation of action. And if you only have a representation of perception, maybe that isn't good enough. Maybe fine-tuning from that isn't good enough for solving, for being able to quickly learn a new task. Okay, so what I'd like to talk about today with this motivation is first, how we can acquire broad and diverse data sets for robots, so that we could allow robots to generalize much more broadly. And second, how can algorithms then try to learn from those offline scalable data sources? So we'll be talking about data and algorithms. So first, let's talk about the data side of things. And on the algorithm side, we'll be looking at both robot data and human data. Okay, so the first thing that we could consider doing when collecting data with a robot is to collect data with random actions. And if you kind of lightly script a policy that's somewhat randomized, you get data that looks like this. And you can actually collect a ton of data this way. You can run robots overnight and get kind of millions of frames. And the data actually is surprisingly rich. And we actually use this data collection technique to really scale and accumulate a broad data set, actually not just within a single lab, but across multiple different institutions. And so we did this across, we were calling this the RoboNet data set, potentially somewhat shamelessly. And we collected this data across 7 different robot platforms. It contains 15 million video frames, 113 camera viewpoints, and it was collected across 4 different institutions. So it actually has a lot of diversity, not just in the robot platform, but in the background scenarios, the objects, and so forth. And it's also something that's open for contributions. It's something that we want to be able to grow in the future. So this is, I think, kind of one way that we could consider scaling data collection. However, random actions don't lead to as sophisticated of behaviors that we might want a robot to be able to do. And so kind of what I'd like to talk about in this first part of the talk is if we can collect such broad data sets, but containing more sophisticated interactions. So one approach for doing this would be to provide demonstrations by essentially having a human guide the robot through certain motions, and you can get, as you see here, interactions that look a lot more sophisticated, a lot more interesting. For example, picking up a tool and using that tool to push objects. So this leads to more useful data probably than random data, but you can't get a lot of it because you require a human to be there for the entire data collection process. It's a very manual process. And so this isn't something that is going to scale quite as readily as autonomous data collection. Now, another potential data source would be videos of humans. For example, here's the Epic Kitchens data set, which has like tons of really rich and interesting interactions of humans performing different behaviors. And so this is lots of really interesting data, but it's of course pretty hard for a robot to use this because you don't have the actions. There's some domain shift between what a human's arm looked like and a robot arm, and maybe the degrees of freedom of humans and robots are different. I'll talk a bit more later in this talk about how we can leverage this data. I do think it's a promising data source, but it's not something that robots can necessarily use directly. Okay, so how can we like scalably collect really useful robot data? And this isn't just a matter of an engineering challenge. I think this is actually also a research challenge. And we started looking into this in a research project that I'll talk about now. So the first thing that we tried was novelty-seeking methods. There's essentially a lot of literature in reinforcement learning on trying to develop methods that can explore their environment and seek out novel situations. And in particular, we positioned this robot in front of this IKEA desk. And our ultimate goal was to get the robot to interact with this drawer. We wanted it to learn how to open the drawer and close the drawer. But ultimately, we would want it to do lots of different things in this environment. And so we took a very recent exploration method that has worked very well in simulation environments and kind of video game type environments as well. And what we found is the kind of interaction that the robot is performing is not actually successfully seeking out all the kinds of things that you might want the robot to do. And in particular, even just like moving its arm in different ways led to the kind of novelty that this algorithm was seeking. And as a result, it never actually, or it very rarely actually reached for this drawer handle right here. So unfortunately, this isn't yet a viable approach, although I hope that we can eventually develop novelty-seeking methods that can explore that. And so at this point, we asked the question of whether a person could help the robot and help show the robot what are interesting things to do such that it can explore in a more targeted way. And critically, unlike demonstration data collection, where the human has to be in the loop for the entirety of data collection, we want to have a scenario where a user can help at the very beginning and then have the robot explore and collect data autonomously for the rest of data collection. And so we want to be able to have a user help the robot without being in the loop of data collection. So the way that we approach this problem is we first had the person show examples of interesting states. So for example, if we wanted to have the robot explore this drawer environment, we would show it examples of reaching towards the drawer and opening the drawer and so forth. And this kind of collection of interesting states would just take a person around a few minutes to do. And then we would learn a classifier that can classify between these interesting states and the data that the robot is exploring. So it's just a binary classifier that classifies between these two kinds of states. And then have the policy try to explore specifically to try to find images that are classified as interesting. And that's kind of the gist of the approach. We give it interesting states, and then we try to have it find things that look more like the interesting states and less like its autonomous exploration data. And what we find is that if we give the robot just less than 3 minutes of human guidance of providing it examples of opening this drawer, and then run the robot autonomously, we then get data that looks more like this, where it is able to actually kind of target its exploration towards this drawer, for example, and kind of sort of play with the drawer in different ways and interact with it in a much more targeted way. And we ran this we were able to run this autonomous exploration overnight. And I think that in just around like 32 to 48 hours of autonomous collection without a human in the loop at all, it was able to collect data that looked like this. And so if you actually also compare the amount of episodes that it actually touches the drawer handle and moves the drawer handle, it's substantially more than this disagreement-based novelty-seeking method. And then we also had experiments in the paper in simulation that showed a number of different scenarios, including interacting with objects, interacting with a variety of objects in the scene, and so forth. Okay, so the takeaway here is that a small amount of guidance can really go a long way towards this sort of data collection, especially when this guidance comes at the beginning of training before the robot autonomously collects data. And then the last thing that I'll mention here is in a follow-up paper, kind of along the lines of reusing and leveraging offline data, we actually took this data set that was collected in this previous paper, didn't modify it at all, didn't collect any additional data, and just directly reused the data set to learn how to train a policy to close the drawer. And in particular, we labeled some images as opening versus closing, trained a classifier which could serve as the reward signal, and then ran offline RL with this reward signal to train the robot to close the drawer. And this is all from image observations. And so the resulting policy that we get looks like this, where the robot learns a fairly robust policy for closing the drawer. This is showing this is a real-time video, so it's not sped up, and it's showing a 76% success rate. So this is an example of exactly what we'd like to be able to do of just having some offline data set and learning from it without having a lot of expensive online data collection. Okay, so that's on the data side. I talked about how a small amount of guidance can really go a long way. And the next step is to really try to scale up this form of data collection and collect much broader data that is both broad as well as somewhat targeted towards the kinds of interactions that we might want the robot to do rather than simply random interactions. Okay, so next I'd like to talk about the algorithm side of things. Once we have a broad and diverse data set, such as the RoboNet data set or such as broad human data, can we leverage that data and learn from those offline data sources in a way that's very useful? So first, let's talk about the robot data side of things. This was before, we haven't, I guess, yet developed a really large data set of like demonstrations or more sophisticated interactions. So we're going to be working with the RoboNet data set that has pretty diverse data in terms of robot data of many different kinds of interactions. And so we wanted to ask, what is the bottleneck for handling these kinds of data sets, and can we train models that can handle this data? And we're going to be taking an approach kind of somewhat similar to what Sonia was talking about, where we're going to try to train a video prediction model conditioned on the robot's actions to generate frames from this data set. And if we're able to train such a model, then we can actually then use that model to get behaviors that optimize some objective. And so here are examples of ground truth robot videos from the robot's perspective. And we then trained this really state-of-the-art video prediction model from Ruben Villegas from NeurIPS 2019 on this data set. And unfortunately, the predictions here don't look very good. The predictions, I mean, in some cases it looks sort of reasonable, but in general, like even the robot arm predictions aren't matching what the robot is supposed to be doing. And sometimes the robot arm predictions are extremely blurry, or it's kind of imagining other arms entering the scene. And moreover, this isn't just the predictions on the validation set. These predictions are representative of what the predictions look like on the training set. And so it's not that it isn't able to capture and generalize to these kinds of videos, it's that it can't even fit the training set in the first place. It's underfitting, which is actually somewhat rare in deep learning, general in deep learning, because typically we're used to having these huge overparameterized models that fit the data well. And this was actually a pretty large scale model. It actually filled up a single GPU, a single 24 gig GPU. And so we wanted to ask the question of how we could try to scale these dynamics models and train larger models without kind of running into these practical challenges and so forth. And one practical bottleneck that comes up is the GPU memory. Even with a small batch size, that previous model was 24 gigs. And so if we wanted to scale the model even more, we would have to do things like model parallelism and so forth, and that would actually involve a lot of complexity and also just significantly slow down training. And these models already take multiple days to train. And so when we were thinking about this problem, there's actually this old trend of training neural networks in a greedy fashion, where you train neural networks layer by layer, where you first train kind of a one-layer autoencoder, and then you train the second layer of that autoencoder to reconstruct the corresponding activations and so on and so forth. And the kind of insights of this kind of model is, first, this kind of model reduces memory costs significantly because you don't need to fit the entire model of end-to-end training, both the forward pass and the backward pass, in your GPU. And I guess the second thing that I'll mention here is beyond memory, these were actually used to alleviate optimization issues. And it turns out that optimization issues also present a challenge for video prediction models because they have a tendency to kind of fit into this local optimum of just predicting the frame that you gave it. Okay, so this is work done by Bohan, and we were thinking about whether we can apply this idea of greedy training to video prediction models. And so kind of at a high level, what the model does is it first trains a one-layer video prediction model, essentially, and then it freezes this layer right here, and then trains another layer on top of it, and so on and so forth. And there's kind of a lot of details in this model, but I'll highlight a few of the high-level bits. So of course, we're training each of these modules, each of these encoders and decoders sequentially and freezing the higher layers of the network. And second, we're actually, instead of optimizing these to match the activations, we're still optimizing them with respect to reconstructing the future frames. And you might ask, well, okay, then maybe this doesn't actually reduce memory, but it does actually reduce memory because you no longer need any sort of backward pass into this part of the network right here. And that actually leads to pretty substantial memory gains and allows us to train much larger models in the same amount of memory. And then one last thing that I'll mention here is that the one thing that we found important in this architecture is to have the encoder compress the spatial dimensions throughout the depth. And the reason why this is important is that when you train these variational autoencoders, there is a prior on your variational distribution that each of the dimensions are independent. And if you have a lot of spatial dimensions and then you flatten that, you're going to have a lot of correlations between neighboring pixels. And that's going to break this assumption that, that every dimension is independent. So this is the mean field approximation in variational autoencoders. Okay, so we asked a number of questions about this model, how they compare to state of the art, do they lead to better downstream planning on robots, and how does this compare to end-to-end training and overfitting? And so we evaluated this model First, just in terms of standard video prediction metrics, including FBD score, which looks at visual quality, and LPIPS that looks at perceptual similarity to the ground truth, as well as just a human preference. And what we find is compared to Ruben Villegas's model, the one that I showed that was like kind of large scale models from 2019, we see a pretty significant boost in prediction quality in terms of all three of these metrics. So we see a 20 to 50% improvement across the board. Now, of course, at least I don't care that much about the video prediction metrics. I care a lot more about what this enables for robots. And so we took this model, we pre-trained it on the RoboNet dataset, and then we fine-tuned it on a small amount of data from this environment, which is actually unseen in the RoboNet dataset because we had to move the robot to a different lab location between working on RoboNet and working on this project. And we tested the model on two different kinds of tasks. One is to pick up the sponge and kind of sweep an object into the dustpan. And the second task is to sweep an object off of the plate. And so what we found is for both of these tasks, using these larger scale models, the greedy hierarchical variational autoencoders, we're able to get a much, much higher success rate than using the model that is really struggling to fit the data, to fit RoboNet, namely. And I guess it's also worth mentioning that we also tried not pre-training on RoboNet and only training on the data that we had in this new lab environment, and that also wasn't able to perform well. Okay, and then the last thing that we looked at is how this compares to end-to-end training and whether these models are overfitting. And surprisingly, we actually found that, at least for this model architecture, end-to-end training didn't perform well at all. And it seems like the greedy training actually leads to an easier optimization problem. And then the second thing that we found is that this model still appears to be underfitting on RoboNet because we see that the training and test loss is still roughly the same, and we don't actually see any evidence of overfitting, at least on the RoboNet dataset. For other datasets that are smaller, we do see overfitting. Okay, so essentially more research is needed to try to still combat this underfitting problem. Okay, so this is an approach for learning from really broad robot datasets and can combat this challenge of underfitting. Now, what about human data? Human data is something where we might be able to get a large number of very sophisticated interactions, potentially just from the internet. And so it's a potentially really exciting data source to use for robots. And it's the goal here that we wanted to be able to handle is actually focusing less on controlling the robot and just looking at the problem of learning a metric of task success or reward function, which is also kind of critical importance to robots, because if we don't have a reward signal or a task success metric, then we can't train the robot in the first place and the robot won't understand whether it's being successful. And we want this metric to be able to generalize across tasks, environments, and viewpoints, unlike something that might be just trained in a single environment, which wouldn't generalize in this way. Of course, there's actually a lot of work on learning from videos of humans. I'm showing some of these works here. However, kind of the vast majority of these works typically use very narrow human data sets with a lot of close similarities with the robot data. And as a result, if you have this sort of narrow human data, you won't be able to promote the kind of generalization that I've been focusing on this talk. And so really, at least for me, one of the big benefits of using human data is this ability to leverage very broad human data in order to promote generalization. So we looked at these kind of in the wild human videos, and in particular, we looked at the something something data set, which is illustrated here. And we wanted to take these human videos and combine it with a small amount of robot data, basically the narrow robot data that we would typically get in a lab environment, and try to combine these data sources and get something that generalizes much better by nature of using these videos compared to only using the narrow robot data. And so we take these videos, the human videos as well as some narrow demonstration data, and we train for a video conditioned reward function that, conditioned on a video of a human, can acquire a reward function that lets the robot know whether it's succeeding at a task. This is during training. And then at test time, we can, in a new environment and a new task, we can use a human video, for example, of pushing this tissue box to the left, to get a video conditioned reward function for that task. and then actually execute the task and learn the task in the real world, potentially in a new environment with a new viewpoint and new lighting conditions. Okay, so this is kind of the problem setup that we're looking at. So how do we actually kind of accomplish this sort of problem? The key idea behind this work is really, really simple. We just train a model that takes as input 2 videos and outputs whether those videos are doing the same task. So for example, if we give it these 2 videos where both the robot and the human are closing a drawer, we give this a label of 1 because they're completing the same task. For these 2 tasks of moving something away versus closing something, we give this a label of 0 and train it to predict a label of 0. And likewise, for these 2 videos, we train it to output a label of 1. So it's just trying to discriminate whether or not 2 videos are performing the same task or not. And it's trained across all of the human data and the narrow robot data that we have available, which is either in simulation or in real. Okay, so we refer to this as domain agnostic video discriminator, or DVD. And we ran experiments both in simulation and in the real world. So I'll start with our simulation experiments. And in particular, we wanted to be able to test generalization to new environments where our initial environment looks like this. We want to be able to test generalization of the reward function to an environment with new colors, with a new camera viewpoint, as well as with the new arrangement of objects. And we considered 3 different tasks in this environment: closing the drawer, pushing a cup to the coffee machine, and turning the faucet to the right. So this first question is, do these human videos allow us to generalize to new environments? And so in particular, what we looked at here is we looked at the baseline methods are the ones that don't use the human data at all. They just use the robot data, which is kind of the standard approach in robot learning. And these, the success rate for each of these approaches is shown in green. And if we actually use this approach to use both the robot data and the human data, these success rates are shown in these pink colors. And we see a large boost in success rate, around actually a 20% boost in success rate on average between using only the robot data and using the human data. And the reason why we see this boost is because we are evaluating for generalization to these new environments, and we just can't generalize to these new environments if we only train on narrow robot data from one environment. And then qualitatively, what this looks like is we give it a human video that looks like this. We then use this to acquire our reward function directly, and then we run planning with a video prediction model to solve the task. And so we can solve this in the training environment, but we can also solve it in environments with new colors, with new colors and a new viewpoint, as well as new colors, new viewpoint, and a new arrangement. Another example shown here is pushing this faucet to the right. We again kind of run the same process to get the reward function, and we also see that this reward function can generalize not only to the training environment, but also to these new environments where the robot can figure out how to push the faucet to the right, even under quite different environments. And then beyond environment generalization, we can also look at generalization to new tasks. And so in this case, we actually held out these tasks from the human data set and the robot data set. And so these are tasks that it had never seen before. And we see that comparing using only robot data to using human data, we see, again, a 20% improvement in task success. And then lastly, we also tested this on a real robot. And so, for example, this is actually both a new environment and new tasks. And so the robot can figure out how to close the door with the video of a human. And likewise, we give it a video of a human of pushing this tissue box to the left, and the robot can figure out how to solve the task. Okay, so to wrap up, I first talked about collecting data and how a small amount of guidance can really go a long way towards autonomously collecting diverse and interesting behavior and data, and also about how generally when we broaden the data, we can achieve broader generalization, and that videos of humans are a promising data source for robotics. And all of these, I think, are steps towards actually getting robots to generalize to a wide range of environments, but we, of course, have a long way to go. I think there's also kind of a number of exciting future and open questions. I think we've barely scratched the surface of data scalability, and more broadly, we can think about not just generalizing with broader data, but also trying to generalize beyond the data distribution. I'd like to thank my students, and I look forward to the Q&A.